Here is a simple artificial neural network. One node on the input layer, two nodes on the hidden layer, and one node on the output layer. Each node is connected to the node next to it. In this series, we will learn to compute what is inside these artificial neural networks, or what is inside the black box. Let's say the weights on the connection lines are -17.5, -3.2, -1.5, and 2. The bias values of the nodes on the hidden layer are 1.25 and 0.5. Meanwhile, the nodes on the output layer do not have a bias value. In this artificial neural network, we will use the sigmoid function on the hidden layer. Meanwhile, on the output layer, it is a linear function. It seems we already know all the required values. To make identification easier, let's call the node on the input layer node 1. The node on the hidden layer is node 2 and node 3. The node on the output layer is node 4. We will analyze the value of each node for each input value. Starting from node 2. This node has a weight value of -17.5, a bias value of 1.25, and the activation function is a sigmoid function. In artificial neural networks, generally the input value is between 0 and 1. When the input value is 0, then the input value at node 2 is x2 equals 0 times -17.5 plus 1.25. The result is 1.25. This value will be processed by the activation function. For the sigmoid function, y2 is equal to 1 over 1 plus e to the power minus x2. Enter the value x2. y2 is equal to 0.77730. To make visualization easier, we can plot these values into two-dimensional Cartesian coordinates. The horizontal axis is the input value at node 1, the vertical axis is the output value from node 2. These are the coordinates of the first point, 0, 0,77730. In the same way, for x is equal to 0.1, for x is equal to 0.2, for x is equal to 0.3, and so on until x equals 1. We have got data from all inputs for node 2. Connect each point, a curve will be formed. Now we will calculate the output value of node 3. Node 3 has a weight value of -3.2, a bias value of 0.5, and the activation function is a sigmoid function. When the input value is 0, then the input value at node 3 is x3 equals 0 times -3.2 plus 0.5. The result is 0.5. This value will be processed by the activation function. For the sigmoid function, y3 is equal to 1 over 1 plus e to the power minus x3. Enter the value x3. y3 is equal to 0.62246. To make visualization easier, we can plot this value into dimensional Cartesian coordinates. These are the coordinates of the first point, 0.0.62246. In the same way, for x is equal to 0.1, for x is equal to 0.2, for x is equal to 0.3, and so on. We have got data from all inputs for node 3. Below is the curve shape of the output values from node 2 and node 3. Now, we will calculate the output values from node 4. Node 3 has a weight value of -1.5 and 2, has no bias value, and the activation function is a linear function. In a linear function, the input value will automatically become the output value. Meanwhile, the input value itself can be calculated through the equation x4 is equal to y2 times -1.5 plus y3 times 2. What does that mean? Multiply the y2 curve value by -1.5 and multiply the y3 curve value by 2. Then add to the curve. This is the curve of y4. The shape of this curve is the black box of this artificial neural network. Knowing the black box of an artificial neural network, we can easily find out the response of the system in various input values. From here we know that the system will be active when the value at the input node is between 0.2 to 0.5. The more nodes on all layers, the more complicated the curve shape will be. The shape of the curve is very difficult to describe mathematically, but can be easily described by varying the weight and bias values, so that the output value matches the expected conditions. We can carry out a learning process to update the weight value. We will study this in the next series.